So, the topic for this particular week is fluid dynamics. Okay. See, last week our total focus is on fluid at rest. Now our focus is on fluid inflow. I told you very clearly, fluid is that nature of matter which have the ability to flow provided pressure difference is maintained. But the flow of the liquid, when a fluid is in flow, the nature of the flow is characterized into four different types. You can say that the flow of a liquid is, I will define everything again, one after the other. Streamlined or turbulent. Fluid flow may be compressible or incompressible, means density constant throughout or density varying throughout. Fluid flow may be viscous or non-viscous. Fluid flow may be rotational or irrotational. These are the basic four classifications to be defined for any flow of a fluid. Now you take streamlined flow, for example. What exactly is a streamlined flow? Now I am observing a fluid element. A fluid element in the flow is flowing like this. I never mentioned it should go in a straight line path. You know, rivers, they won't flow in a straight line path. They will move like this only. So a fluid particle is going like this. You can imagine like something which you are sending through a tube. For watering purpose, you will use a tube. That tube I am speaking about. You take one such element here. Every fluid element, whichever arrives to 1, will have velocity v1. Remember, any element that comes at 1 will have the same velocity, same direction. Any element that comes here will have the same velocity, same direction. Any element that comes here will have the same velocity, same direction. I am repeating again. I am following one fluid element. That fluid element at 1 will have v1 velocity. That fluid element at 2 will have v2 velocity. That fluid element at 3 will have v3 velocity. In fact, I am tracing the path traveled by a fluid element. That imaginary path is what we will call as a streamline. And the flow is said to be streamlined, that every element that comes here follows the same rule. Such a flow is called streamlined flow. If every fluid element following this path as same as the path followed the first fluid element, such a flow is called streamlined flow. The path traveled by a fluid element is what we will call as a streamline. You can observe all such things during Republic Day parades or Independence Day parade. You can see that. As I'm just giving an example. All first soldiers, if they are raising their right leg up, every soldier in that group will do the same. Likewise. No collection of such streamlines will make a tube of flow. This is all we call as a tube of flow. Suppose if any fluid element is not satisfying this condition, different velocities at point 1. One fluid element will have a velocity v1 at 1. One fluid element will have a velocity v1 dash at the same point. Different velocities, different directions. Such a flow is called turbulent flow. Usually when the river flow is very high, you will see turbulent flow. A collection of streamlines is a tube of flow. Till this point, any doubt? Every student in this class. Next. Now you take an element, a fluid object otherwise. It follows a path like this. you place a floating object on this, a sphere like kind of object, for example, a wooden block kind of object on this. What will happen now is that this object will trace the path like this. And this is one streamline. But as long the particle or the object is traveling, it's not rotating, it's purely translation. Such a flow is irrotation, which means on the flow, you can see that during canals, sometimes calm, slow water flow, you place a floating object, a thermocol, something like that. You will see that the thermocol will be translating, but it won't have any intrinsic spin. If it is translating along with the intrinsic spin, then in that case it is not irrotational. That will be rotational. So I have introduced the two things: streamline, turbulent, rotational, irrotation. Next, if the density of the flow remains constant throughout, such a flow is called incompressible. Density point to point changes, it is compressible. Okay, now? Next. Discuss, anyway, next chapter we will discuss that one. Next chapter we will discuss that one. Right. There is a special name called ideal flow. Any flow which is streamlined, irrotational, incompressible, non-viscous, such a flow is called ideal flow. Okay? Right. So I have just defined what exactly is an ideal flow. Now we will enter into the chapter. The chapter starts with the equation of continuity. Now you see there is a tube of flow like this. There is a tube of flow like this. Now please try to understand at the entry point. If I question you, what is the mass of the liquid entering per second? Actually, this is simply a tube. There is no leakage or there is no source also in that. You are not connecting this to any tank. Please write except the exit and entry points. No portion of the tube is connected to any tap. No portion of the tube has a hole, a sink otherwise. So therefore, in that case, whatever enters at the entry point must leave the exit point. So per second, whatever the mass enters at the entry point, that should leave the exit point. That is the rule. Now the question is, fine. What is the mass entering per second? For this purpose, I am assuming the density of the liquid at this point. At this point, density is equal to ρ1. So at this point, density is equal to ρ2. So ρ1, what is mass? Otherwise, mass means density times volume. So in a dx1 width with A1 cross-sectional area, what volume is enclosed? A1 dx1. You are speaking about rate. So therefore, ρ1 A1 dx1 by dt is equal to, that is mass leaving per second, ρ2 A2 dx2 by dt. dx1 by dt is called V1, dx2 by dt is V2. So this particular equation, ρ1 A1 V1 is equal to ρ2 A2 V2. Remember, this equation is applicable under only two conditions. One, I assumed the flow to be streamlined. I assumed the flow to be irrotational. Only these two conditions are assumed, which means, suppose if the flow is viscous, no issues, you can still apply. Suppose if the flow is compressible, you still can apply. because I have mentioned in terms of density. Sir, I am adding another feature. You added two features only right now from ideal flow. What is that? Streamlined flow and irrotational. What if it is incompressible? Density must be same. If it is liquid, water, something like that, you can simply use A1 V1 is equal to A2 V2. And this is the equation of continuity which we will apply for liquids. For gases, mostly we will apply this. For liquids, we will apply A1 V1 is equal to A2 V2. Till this point, any doubt? Any student in the class? Pakka. Right. Right. Next. I'm just introducing basics of this chapter again. For a massive object, suppose if you look at an object, a small block, a small sphere, if I project that object into the air, I simply speak about only two forms of energies. One is because of height, gravitational potential energy, because of flow, translational K. Right. So basically, I speak about KE and PE for a object, a materialistic object. But for a flow, there is another energy which is called pressure energy. So how do I feel pressure energy? Simple. Now you consider a container like this. This is all a container. But there is this opening here, and this opening part is closed by a piston connected to some spring type of arrangement. Now what is happening is, initially the spring might be relaxed. Just because that you have connected here, this piston got pushed rightwards. Someone is doing work there. Who is that? Pressure force. The capacity of doing work by the pressure force at that point, capacity of doing work is energy, is what we will define as pressure energy. So therefore, at this point, work done by pressure force, you will simply write it as dW is equal to PdV. So pressure force does work at that point, and that work done by the pressure force is stored in the spring as a form of potential energy. Till this point, any doubt? So I have introduced pressure energy to you. Already you know, by flow you will have kinetic energy, by height you will have potential energy. If, for example, a fluid element here versus a fluid element here, definitely, as far as gravity point of view, it has more energy than at this point, right or not? So please try to understand, these are the three different forms of energy that a fluid element will have. Whereas for an object, you will refer only two forms for mechanical energy. For a fluid, you will refer three elements, three forms. What are they? Pressure energy, kinetic energy, gravitational potential energy. Any doubt till this point? Everyone in this class? Now I am applying Bernoulli's equation. Remember, Bernoulli's equation is strictly applicable for ideal flow. Sir, flow is viscous. Don't apply Bernoulli's equation. Flow is irrotational. No issues. But other three factors must also satisfy. For an incompressible, no, don't apply Bernoulli's equation. Compressible, don't apply. Rotational, don't apply. Viscous, don't apply. Turbulent, don't apply. If 4 lo okati tagilna chalu, you are not allowed to apply. So Bernoulli's equation, I am taking an ideal flow. For an ideal flow, like maybe there is a pump mechanism here, and it is a pumping liquid out through this. So it is doing a regular constant work, right? Or else overhead tank ekkadakada undi, overhead tank. I took the pipe like this. overhead tank is doing work right now, right? For an ideal flow, the total energy per unit volume at any point of flow is a constant. For example, at this point, per unit volume, pressure energy is P1. Why? You said rate of doing work done is PdV. Delta W by ఇక్కడ దీన్నే ప్రెషర్ ఎనర్జీ పర్ వాల్యూమ్, వర్క్ డన్ పర్ యూనిట్ వాల్యూమ్ కదా అక్కడ, కాబట్టి ప్రెషర్ ఎనర్జీ పర్ యూనిట్ వాల్యూమ్. సో యూ హ్యావ్ at this point I'm assuming the pressure as P1, at this point velocity V1, I'm assuming that this is to be height H1. Then what to Bernoulli's equation is referring over here. At this point, pressure energy, kinetic energy, potential energy. At this point, pressure energy, kinetic energy, potential energy. Any doubts? Clear? This is Bernoulli's equation. Bernoulli's equation applications is vast actually. So now I am discussing about the different applications of Bernoulli's equation. Everyone wants to go through Bernoulli's equation once.